Salam and a very good day to you. This is Amina Tahreen, a postgraduate student from International Islamic University, Malaysia, Faculty of Engineering. So the topic that I'm going to be discussing today in this conference is Advances in Antifouling Strategies for Membrane Ultrafiltration, a brief review. Let's get started. So basically, I'm dividing today's conference, my presentation, into four parts. First, I'm going to be introducing about why I'm so interested in antifouling strategies, and it is related to membrane technology. Second, I'm going to talk about the current methods for devising these strategies. Third, the recent notable advances in the technology, and number four is conclusion. So basically, membrane technology is one of the fastest growing fields because it has remarkable contribution in separation and purification technology. So basically, separation and purification are one of the most important technologies because we need it from pharmaceuticals to water and wastewater treatment. So for example, you can see why it is so important because of these four important features. First of all, selective separation, compact design, small footprint, and environmental friendly. Selective separation because, as you can see, this is a schematic of a membrane layer. It can be designed and modified to fit, be selective in its pore size and materials, so it can separate to the desired purity. Another one is compact design and small footprint. Because of its compact design and small footprint, it does not require huge space to carry out its function. So that makes it really desirable in the industry. And lastly, it's environmentally friendly. It is not, membrane technology does not require harsh chemicals and does not produce harmful byproducts that can cause harm to the environment, and therefore provides an environmental protection factor. So there are two main modes of operation, crossflow and dead end. Crossflow operation, it is important to know these two types of operation of a membrane, and both of them have their own advantages and applications. For example, crossflow filtration has more application towards continuous operation, and dead end on the right, it has more advantages on, purification of small proteins or, in pharmaceuticals where we don't require continuous operation. So in crossflow filtration, the difference between both of them is obviously one of them is continuous and the other one is also continuous, but the difference is in the layer of cake formation. Basically, the deposited foulants here is basically the foulants or the pollutants that build up over time of a membrane operation that stops the flow, that reduces the flux. Flux is basically the flow rate per unit surface area of the membrane. And over time, if it reduces, that means the membrane is losing its efficiency over time. For example, here the feed is one of the pollutants, industrial effluent, palm oil mill effluent. In a crossflow mode of operation, the cake layer is constant because there's a turbulence in the flow, turbulence on the surface of the membrane. And on the other side, in the dead end, you can see it is legit a dead end. Okay, so the feed is coming vertically towards the membrane, and over time, a cake layer is building up. So what happens? What can we expect here is over time, the flux will reduce until it will stop because the membrane pores are completely blocked, and we cannot allow that in an operation that is so important, especially water and wastewater treatment. So it is important after learning the mode of operation to learn the type of pore blocking. And there are four main types of pore blocking, and these models have been devised by Hermia, and these are very important because it gives us an understanding of the types of fouling that takes place. It helps us understand the mechanism behind the fouling. So if we can understand which kind of blocking is taking place, it will help us better to come up with an antifouling strategy. So four types of pore blocking that takes place in every membrane filtration system is complete. It could be either complete blocking, standard blocking, intermediate blocking, and cake filtration. So from this diagram, you can actually have an idea of which one is the worst from just visual monitoring. Cake filtration is obviously the worst one because you can see as the cake layer is building up, the flux will become zero and the whole membrane filtration process is going to be dysfunctional. So therefore, it will cause a reduction in flux, membrane integrity will be lost, and the process times will obviously increase because now there is less space and more pollutants blocking the way for the clean effluent. So now comes to the point, the antifouling strategies. Fouling is basically, let me just give a quick review. Fouling is basically the blocking of pores with the pollutants, could be organic, inorganic pollutants that are blocking the pores and causing these obstacles for the membrane performance. So there are four main types of antifouling strategies that have been uh, used over time and researched, constantly researched. First and foremost is membrane cleaning. So there are two types of membrane cleaning that are very commonly used for a long time. It's physical and chemical. So basically the physical membrane cleaning involves assistance from air, ultrasonic, high pressure air aided physical cleaning systems, and then ultrasonic and also hydraulic. Hydraulic systems use frequent backwash, etc. And another one from the chemical side is basically use of frequent chemical cleaning with acids, alkali, oxidants, surfactants, and many more reductants like hydrogen peroxide, very harsh chemicals. In my opinion, the physical strategies are more environmentally friendly than chemical because there is an environmental toll that these chemicals are bringing about when the frequent cleaning of membrane. One of the drawbacks of physical membrane cleaning systems are the use of high pressure. High pressure, it can incur a lot of energy, the power consumption, and therefore the costs. So we need to balance out, which one has the the lowest risk with the highest output. All right, so next, moving on to the next type of fouling strategy is inhibiting foulant migration. Basically, this strategy is to modify the pollutants that are settling on the membrane surface. For example, how? By controlling the flow hydrodynamics, by using high intensity spiral flow, integrating movable parts. Basically, this is the strategy of controlling the movement of the foulants by manipulating the flow. For example, if you are providing a very turbulent flow of the feed that is going inside the membrane, it will obviously cause a disruption and turbulence inside the membrane, and it will not allow the foulants to easily settle on the membrane pores and cause fouling. And second one is, for example, high intensity spiral flow is one of the examples. And third one is integrating movable parts. Integrating movable parts inside the membrane system can be pretty complex because if you want to do a troubleshoot of the membrane, it will become very hard to assess. But the main aim of integrating those parts is also to create turbulence in the membrane to actually inhibit the foulant migration. So the third one is pretreatment. I think pretreatment is one of the most interesting processes that have been integrated in membrane filtration as a part, and it can be considered as a part of antifouling strategies because they are reducing the foulant, the pollutants, to a huge amount so that the remaining treated sample goes inside the filtration, and that will remarkably drastically reduce the fouling in the membrane. So the pretreatment processes, there are huge research is done on different types of pretreatment. There are physical pretreatment experiments. For example, adsorption. It reduces a huge amount of the targeted pollutants, and it can be also very selective by using the different types of membrane and adsorbents. Chemical treatment. There are also many chemical pretreatments that have been widely used for as a prior process to membrane cleaning. For example, chemical treatments are like chemical coagulation. It requires adding coagulants and flocculants to really remove the organic foulants from the wastewater. So that can be photochemical. This one is also interesting. Photochemical, it requires, addition of it can be UV or, solar irradiation to remove a lot of foulants prior to membrane filtration. And the last one, one of the striking ones, is electrochemical. This is also one of the works that I've been working on, is electrocoagulation. It removes a wide range of waste pollutants, like not only starting from heavy metals to organic foulants to a wide range of wastewater that it can treat. So it is one of the most reliable, promising pre-treatments for membrane that can be integrated with membrane technology. And last but not the least is the membrane surface modification. This is one of the growing fields of antifouling strategies, because here the aim is to modify the membrane surface in terms of their electrostatic attraction and their substrate modification, how they are attracting to the foulants and the substrate. So basically, this is possible by Membrane substrate modification. In membrane fabrication, you fabricate the surface in such a way that fits the hydrophilicity or hydrophobicity of the target pollutant, right? So this can also be done by surface grafting of polymers. Surface grafting of polymers is basically you are grafting the hydrophilic polymers, different types of uh, compounds that will interact with the foulant. So basically in your membrane surface, you're going to be, it has grafted polymers that will enhance the hydrophilicity to support the easy movement of the required permeate, right? And reduce the antifouling. Reduce the fouling, enhance antifouling. Gets a bit confusing. And the last is alteration of membrane geometry. So there have been a lot of researchers that modified membrane roughness, their geometry, in a way that enhances the antifouling strategies. So basically, I'm going to talk about now some recent notable advances in the antifouling strategies. So I have gone through a lot of works, and three of these works had stood out the most. So first is basically grafting graphene oxide. So basically, graphene oxide forms a nanosheet in a hexagonal shape, and it has a nanosize effect because of its small size and flexibility. So it was an amazing work where 94.2% of fouling recovery was achieved. It was worth exploring more, and it actually is opening new insights to graphene oxide and antifouling. Basically, in this image, you can see how grafting process uh, takes place. This is a visualization of what do I mean by grafting on membrane. For example, here, this is the membrane surface with the pores in it. Usually all grafting processes take place by initially uh, coating it with polydopamine. After coating it with this polymer, polydopamine, the hydrophilic or the desired polymers are grafted on top of this layer. So these graftings, as you can see, they'll have these charges that is going to be very suitable, the desired charges for attracting and attracting and repelling the target materials or the pollutants, to facilitate the desired purification. So in this grafting, there's graphene, titanium oxide and fluoride, and then polysiloxane. There are many different types of grafting that had been studied over the years, but these are the three the recent advances that I had that was very outstanding. So titanium oxide and fluoride incorporation, this is also one of the impressive advancements in this field, because the flux ratio was increased to 80% with solar irradiation and self-cleaning. The best part about this work was it was able to self-clean. Imagine if you're creating a system that has the ability to self-troubleshoot. That is the point I'm getting from self-cleaning here. And it was very interesting because titanium oxide and fluoride clusters under solar irradiation were able to create and generate hydroxyl radicals. These radicals are able to react with the foulants in the membrane surface and break them down. So this degradation reduces the fouling. And in that study, it reduced by 80%. So this was pretty impressive because I can see a promising future with this technology because of the self-cleaning and automation with this incorporation of fluoride. So third one is polysiloxane grafting. Polysiloxane is another polymer that has been grafted on the membrane surface in a similar way. First, there's polydopamine coating, and then grafting of polysiloxane. So the fouling rate was lowered by 70%, and it's huge for this process. So lastly, we're at the end of this presentation. What I have concluded from this study, from this review, was that there have been meaningful progress, in polymer grafting and membrane surface and solar irradiation. And the most promising research direction, I believe, is the studying of pore blocking and antifouling modeling and assessment of harmful byproduct release. So basically, as we are incorporating fluoride, polysiloxane, graphene oxide on our membrane surfaces, we are producing amazing results in the end. But we need to also think about environmental aspects of it. Is there any release of those chemicals in our final product, or is there any leaking of these radicals that are being using in the self-cleaning process, and also antifouling modeling. The new research direction can be also towards modeling of these processes, so that we can expect some outcomes with modifying, like changes in parameters, like how will this model be responsive to situations that are unknown, or that we can predict or create. So pore blocking models, because pore blocking models, we need to create this for different kinds of wastewater, because this helps us determine the best pore blocking that is taking place, and take the antifouling strategies accordingly. And assessment of harmful byproduct release is one of the most important factors as well. So this is my conclusion for this review that I had carried out for this conference. And there we are towards the end of this presentation. So a quick overview. Basically, I've introduced about the membrane technology and why is it important and what are the obstacles to it. And the obstacle is obviously fouling that takes place, because of which we need to come about with antifouling strategies, which is here. So I talked about 4 different types of antifouling strategies that are in place, starting with membrane cleaning, which is physical or chemical, and second about modifying the migration of the pollutants before settling on the membrane surface and pores. Third, the third one was about pre-treatment. I'm also working on one of the pre-treatment methods for prior to membrane filtration. And the last one is about membrane surface modification. So the recent advances, I've highlighted three notable advances that are very recent and remarkable, that have achieved remarkable results in recovering fouling. And to conclude, I believe we should go towards environmental protection and the release, also the upscaling. We also need to study the upscaling of these processes towards industrial scale. And that's where we also need to look at the modeling as well as the pore blocking studies, because pore blocking studies not only helps us to identify the mechanisms that are working to create the type of fouling in a particular filtration system, but also they help us with the parameters to upscale it, not only upscale, and to facilitate the specific antifouling strategy that we must follow. So there you go. Thank you very much for listening to this presentation, and looking forward to Q&A.